Okay, so the next speaker is Dmitri Tseluiko from the University of Loughborough, who's going to talk on the transition to dripping of an inverted liquid film.
Okay, thank you. So I'll talk about the transition to dripping on an inverted liquid film, and this collaborative work with Mark Bly, Tashen Lin, Serafim Kaledasis, and Radu Kimpeanu. So in this talk, I consider flow on the underside of an inverted plate, and most of the research focused on the flow on the upper side of an inclined plate, but flows on the underside of inclined surfaces or just underside of surfaces are also important in various applications, and the interest is in analyzing such flows has been growing. The applications are, for example, in liquid film coating, in cooling systems, in falling film evaporators, which arise, for example, in refrigeration, chemical and petroleum refining industries. So if we consider first a liquid film flowing down a vertical wall under the influence of gravity, then it is well known that in the absence of inertia, the flow is stable. This is a well-known result by Benjamin and Yi. But if the angle is increased beyond the vertical value, the film becomes partially inverted and thereby susceptible to the gravitational Rayleigh-Taylor instability. And the disturbances, linear disturbances, initially grow, and then they become dominated by nonlinear effects, and eventually they are saturated into traveling localized waves or droplets, as can be seen in the experiments of Brun et al. In this photograph. But common experience suggests that if the inclination angle is sufficiently large, then the disturbances do not saturate but continue to grow, and eventually this can lead to dripping. So the droplets detach from the film surface and fall down. And our motivation is to analyze this transition to dripping. Okay, let me first mention some previous work on inverted liquid films. So Rothrock, in his PhD thesis published in Cambridge in 1968, analyzed stability of an inverted film based on a lubrication approximation, and he obtained on-set conditions for the formation of the waves as well as their wavelengths and speeds, and he compared his theoretical results with his experimental work. And then further experimental and theoretical study was done by Indeikina et al. On drop formation on pendant rivulets, and the analysis, the theoretical part, was also based on a linearized curvature model thin film equation. Tashen Lin and Lou Kondich in 2010 analyzed the role of the fronts and associated contact lines on the instability formation and the formation of waves, and this was extended to 3D in 2012. Karogiannis and Markidis analyzed experimentally the temperature effects on liquid films flowing over inclined planes, and then this was also extended. Some preliminary work was done on inverted liquid films, experimental work. And there have been several works which analyzed the absolute and convective nature of the instability, and these suggested that transition from the convective instability to absolute instability may be related to the onset of dripping. And these works include the one by Brun et al., Shade, and Tomlin, Kimpeanu, and Papageorgiou, where the latter one also analyzed the effect of the electric field acting in the direction of the flow. But we suggest that dripping must be a fully nonlinear phenomenon, and it's unlikely that it can be adequately described by a simple transition from convective to absolute instability. So we instead suggest that to analyze dripping, we can compute Trown wave solutions by a continuation method, and we expect some kind of a breakdown at some critical angle, let's say. And some preliminary approach was done. Some preliminary work along these lines was done by Kaufman et al. In 2018, who computed Trown wave solutions for the fixed volume case using several weighted residual integral boundary layer models. which allow for the effects of inertia at finite Reynolds number. And some results are shown in this picture. So for one of their models, it can be observed that as the inclination angle is increased, so gravity here points upwards. Yeah? As the inclination angle is increased and the plate tends to become more horizontal, the amplitude of the waves grows and the waves adopt the shape of localized droplets. And relevant study was also recently done by Zhu and Prosperetti in 2022, who performed time-dependent simulations using the open source software Basilisk. And they, again, considered the fixed volume case with periodic boundary conditions. And then they analyzed full time-dependent solutions where they gradually changed the inclination angle during the simulation. And they were able to compute quasi or near travel wave states. An example is shown here, and they observed that waves, there is a droplet formed in the middle of the computation domain, and this droplet remains stable if the inclination angle is not too large, but when the inclination angle becomes sufficiently large, the droplet detaches from the surface of the film and dripping occurs. And they suggested that the detachment process is associated with the point at which the curvature at the tip of the droplet becomes larger than the curvature which corresponds to the maximum volume static Young-Laplace solution for the fully inverted plate. But using such a criterion, so the tip curvature as an indicator of dripping is probably not so convenient in practice because it cannot be easily computed. So there remain two issues. The first one is to provide an indicator which can be easily measured and used in practice, and the second one is to provide a rigorous justification of such an indicator. And so we suggest to do this by computing travel wave solutions. So here is the setup that we analyze. So we consider liquid film flow down the underside of a plate, flat plate, which is inclined at an angle beta to the horizontal. So we consider two-dimensional flow. We introduce Cartesian coordinate axis x tilde and y tilde. Tildes are used to indicate dimensional variables. And as I've already mentioned, as the inclination angle is increased and the plate becomes more horizontal, the amplitude of the waves grows and dripping may occur. So for simplicity, we want to analyze the transition to dripping, so we ignore inertia and assume that the flow is governed by incompressible Stokes equations. We impose the usual no slip and no penetration boundary conditions at the wall, and at the interface we have the usual stress balance conditions. So capital T here is the Newtonian stress tensor, P tilde and U tilde are the pressure and the velocity in the fluid, and sigma is the substantial coefficient, kappa is the curvature of the interface, and we have the usual kinematic condition as well. So it's convenient to non-dimensionalize the equations so that the scales do not depend on the inclination angle, because we are going to vary this angle. And to do this, we non-dimensionalize distances by the Nusselt flat film thickness for the case of a vertical wall. And the velocities are non-dimensionalized by using the Nusselt surface speed. The ratio of h star and capital U, so this length scale and velocity scale, is used as the time scale, and for the pressure scale we use rho g star over 2. And this reveals the dynamical importance of the bond number, which measures the relative importance of gravity to surface tension. And in the usual way, if we assume that the variations in the streamwise direction occur over a much longer length scale than the film thickness, we obtain this thin film equation, where Q is the flow rate given here. So the first two terms correspond to the effects of gravity in the streamwise and cross-stream directions, and the last term corresponds to the effect of capillarity. Kappa here again is the curvature. And we are interested in analyzing travel wave solutions to this thin film equation. So we rewrite this equation in the frame traveling at the speed of a traveling wave, c, and then we obtain that traveling wave solutions must satisfy this ordinary differential equation. So in the formal derivation of this long thin film equation, curvature is approximated by the second derivative of the interface, and this leads to the first model, the linearized curvature model, or LCM. But we will also use this ad hoc model where the linearized curvature is replaced by the full curvature, and this leads to the full curvature model, FCM. And we are going to consider two scenarios, both of which are relevant to applications. The first one is the fixed volume case, where we assume that the volume is fixed in the computational domain. So the integral of h from minus L to L, where minus L to L is the computational domain, is fixed and equal to V. And in the second scenario, we assume that the flow rate is fixed. And we assume that flow rate, the dimensionless flow rate, is equal to 2/3, which in our non-dimensionalization corresponds to the flow rate of a liquid film flowing down a vertical wall of unit thickness, that dimensional thickness equal to 1. And if the inclination angle changes, then in the far field, the thickness should also change to maintain the same flow rate. And it turns out that the flow rate, the thickness should be equal in the far field, so upstream and downstream should be equal to 1 divided by the cubic root of 1 divided by the sine of beta. So in our computations, then we impose this thickness upstream and downstream. And actually, so for the linearized curvature model, these two cases, the fixed volume and the fixed flow rate cases, are equivalent. And this can be established by noting that if the thickness is rescaled by its far field value, and if the streamwise coordinate x and the wave speed are rescaled as shown here by using the inclination angle beta and the Bond number, then this leads in both cases to the same equation with the condition that thickness should tend to unity at infinity, upstream and downstream, provided that the value of this parameter gamma, depending on the inclination angle, the far field thickness, and the Bond number, is the same for both cases. Okay, and actually, it turns out that the same equation was also derived by Kaliadasis and Chan in a different context, namely to study drop formation on vertical fibers. And they obtained asymptotically that solutions to this equation blow up as c tends to infinity and gamma approaches this critical value equal to 0.596. And this equation was later revisited by Yu and Hinch, who provided higher order corrections to the asymptotics of Kaliadasis and Chan. So we can use this for our work. So the implications are the following. So for the fixed volume case, we obtain that as the inclination angle tends to beta, the far field thickness or the precursor thickness for the fixed volume case tends to 0 and scales as pi minus beta. And the wave speed also tends to 0 and scales as pi minus beta to the 3/2. For the fixed flow rate case, it can be easily then concluded that there is a critical angle beta c at which solutions blow up and this critical angle beta c can be obtained as the solution to this nonlinear equation. So for each flow rate at each bond number, we obtain a different critical angle. And this critical angle then must correspond to dripping. It must be related to dripping transition. So beyond this value, we expect that no triangle wave solutions exist and dripping must occur. But I should note that such equivalence is only possible for the linearized curvature model. For the full curvature model, there is no such equivalence, so we should consider the fixed volume and fixed flow rate cases separately. And there is no such equivalence also for the full Stokes equations, solutions of which I will also discuss later. Let's consider first the fixed volume case, and let's consider the case when the plate tends to become horizontal. In this case, as I've discussed on the previous slide, we know that the thickness of the precursor film tends to 0, and then the solution must approach the solution of the static Young-Laplace equation, which represents balance between gravity and self-extension. And the Young-Laplace equation for the full curvature case is shown here. Here A and B are simply the parameterizations of the free surface, and S is a parameter. For example, it can be the arc length. And the left panel here shows the bifurcation diagram of solutions to the static Young-Laplace equation. This was also analyzed by Pitts in 1973. So for the linearized curvature model, the Young-Laplace equation is a linear equation, and solutions are just sinusoidal, have sinusoidal shape. And they exist for any value of the volume. So we plot the droplet height over the volume. So solutions exist for any value of the volume. These are shown by the dot dashed line, the respective curve. But for the full curvature model, we find that there is a turning point in the solutions curve. And we scaled here the volume and the height by bond number. So it turns out that the turning point is at approximately 2.6. So the scaled volume equal to 2.6. So if the volume is larger than this value, then self-extension is not strong enough to act against gravity, and we must have dripping. So the lower part of the solution curve corresponds to stable solutions, and the upper part corresponds to unstable solutions. So the right panel shows several solutions. So the solution, the maximum volume solution corresponding to this diamond, is shown by this dotted line. And then the solid line and the dashed line correspond to volume equal to 2. So the solid line is the stable solution, and the dashed line is the unstable solution. And also at this filled circle, the solution becomes self-intersecting, so the solution pinches, and there is no physical sense to continue beyond this point. The respective solution is shown by the dot dashed line here. Now we want to discuss asymptotics when the inclination angle is not quite pi but approaches pi. So we do it for the full curvature model. So basically this is an extension of the analysis of Kaliadasis and Chan. And we match the drop region R2 with the flat film regions R1 and R3 via the transition regions B1 and B2, where the problem reduces to the well-known Brotherton or Landau-Levitch equation. So, and we choose asymptotic expansions so that we can obtain consistent match between the different regions. So it turns out that in the drop region R2, the expansion as shown here, we have H0 plus a delta correction plus delta to the 3/2 and so on. So H0 is just the static Young-Laplace solution of volume of the given volume. H1 is obtained as the solution of the linear equation with the coefficients which depend on H0, And then turns out that at the next order, H2 has this singular behavior at the edges of the drop, and this is exactly why we need to introduce the transition regions B1 and B2, where the problem reduces to the Bretherton or Landau-Levy equation. And then it turns out that the speed again scales as delta to the 3/2, where delta is simply pi minus beta. And in the film region, the film thickness scales as delta. And these coefficients C0 and HP0 in the leading order solution now for the full curvature model depend on the volume and the bond number. This is unlike for the linearized curvature model, where these are universal constants. So we need to obtain these values for each value of the volume and bond number. For example, for the case which I'll consider on the next page, when volume is equal to 8 and bond number is equal to 0.3, the coefficient in the leading order precursor film is 1.8, and the coefficient in the leading order speed is 2.83. So these are computed numerically. So now I'll discuss some numerical results. So for we compute Brown wave solutions, branches of Brown wave solutions for the full curvature model and the linearized curvature model using a numerical scheme based on Newton iterations and pseudospectral representation of derivatives. And in addition, we also compute solutions, Brown wave solutions, to the full Stokes equations using a boundary element method. And we consider two different cases, so the fixed volume case and the fixed flow rate case. And basically we change the inclination angle, and as the measure of the solutions, I just plot the droplet height over the inclination angle. So the first case that is represented here is the fixed volume case when the bond number is equal to 0.3 and the volume is 8, so that the scaled volume, the product of bond number and volume, is 2.4, which is less than the critical value 2.6, so that the limiting Young-Laplace solution exists. And indeed, in this case, we obtain that solutions can be continued all the way to pi. And there is very good agreement between the full curvature and linearized curvature model for smaller values of beta, but then we obtain discrepancy between these models for close to pi. And on the other hand, the full curvature model agrees very well with the full Stokes equations for values of the inclination angle close to pi. And this agreement between all these models can be made better when we consider a smaller bond number. And so solution profiles at beta close to pi are shown in this plot, where we indeed observe good agreement between the FCM and Stokes solutions. And we also compared our numerical results for the FCM model with the asymptotic analysis, and indeed we find very good agreement. So here we plot the speed and the precursor thickness over pi minus beta on the log-log scale. So the black solid line corresponds to the numerical solutions, and the dashed line corresponds to the asymptotic prediction, and we find very good agreement. If the volume is increased for the same bond number, then we find that, for example, when we take volume equal to 15, so that the product of bond number and volume is 4.5, which is larger than 2.6, then limiting Young-Laplace solutions do not exist anymore. And what we find is that there are turning points in the bifurcation diagrams for the FCM model and for Stokes solutions. But of course, the linearized curvature model can still be continued all the way to pi, and the respective solutions have sinusoidal shape. So the FCM model terminates at the point where the curvature of the interface becomes infinite. This is confirmed in the right panel. So the zoom in of this region is shown in the inside here. And we cannot continue beyond the point where the curvature becomes infinite for the full curvature model. Yeah? The model breaks down, but we can go beyond this point for the full Stokes equations, and in this case we obtain multi-valued solutions. So we can continue all the way to this value here. And the most extreme solution for the Stokes case is shown in this panel by the dashed line. So it resembles a droplet which is close to pinch off and the subsequent dripping. And also in this panel, the green dotted line is the solution at the turning point, and the blue solid line corresponds to the same value of the inclination angle as this extreme solution, but on the lower branch. So this is the stable solution for the same value of the inclination angle. Okay, now we consider the fixed flow rate case, and then first let me consider the small Bond number value equal to 0.05, and the linearized curvature model has a blow up at beta equal approximately to 3.022. This value can be obtained from the asymptotic analysis, but the FCM model and Stokes solutions, bifurcation diagrams for Stokes solutions, have turning points at values before the blow up of the LCM model. The FCM model again terminates at an infinite slope singularity, but generally it predicts the correct qualitative behavior, although the turning point for the FCM model is delayed compared to the solutions of the Stokes equations. And overall, we can conclude that both FCM and LCM and FCM model give quite a reasonable estimate for the value of the angle beyond which traveling wave solutions do not exist, and beyond which we expect dripping to occur for the case of small Bond number. Okay. Now, if we consider a larger Bond number, then the linearized curvature model still blows up at a certain value. Now, this value is 2.638. This value can again be obtained from the asymptotic analysis. However, for this larger Bond number, now we find that the FCM model breaks at an infinite slope singularity before reaching a turning point, and well before the blow up of the LCM model. And even worse situation is with the Stokes solutions. Stokes solutions can be continued only up to approximately 3.74. Somehow our numerics breaks down at this value, and we are not fully sure what happens at this point. What we can observe that solutions for Stokes equations become multivalued well before the breakdown at this value, and actually for smaller values of the angle, there is an eddy which is confined to the near tip region of the wave, but when the inclination angle approaches this critical value, the eddy inside the pulse increases, and the rightmost stagnation point moves downwards to the heel of the pulse, and we computed the curvature at this point, and we found that it increases. So one hypothesis is that we may be approaching a cusp singularity at some critical angle, and that's why our computations break down, or maybe there is a very sharp turning point which we were not able to resolve with our current numerics. So this is ongoing work. And to understand better what happens at this critical value, we also performed time-dependent simulations using the open source software Basilisk. So we used this particular fluid, silicone oil, and we chose parameter values so that the effective Reynolds number based on the average film thickness is small, so that it is appropriate to compare full time-dependent simulations with the results for Stokes equations, which I discussed previously. So it is convenient to do full time-dependent simulations using fixed volume and periodic boundary conditions. So what we did, we want to analyze what happens for this fixed flow rate case. So to do this, we basically extracted this most extreme solution for Stokes simulations, computed the volume for this most extreme solution, and used it for our time-dependent simulations. And we looked at solutions for different angles. So here are some results. So this is what happens when the inclination angle is smaller than the value at which our Stokes simulations broke down. And what we find is that the solution converges to a traveling wave, which has the formula for localized droplet. Then we basically increase the inclination angle. Now it's equal to 2.38, which is now beyond the critical value. But still, we find that the solution converges to a traveling wave. So this value is slightly beyond the critical value. Now we go a bit further beyond the critical value, and in this case, we find that basically dripping occurs, so the droplet continues to grow and then detaches from the surface of the film. So somehow we find that the point at which our Stokes code broke down is closely related to the transition of dripping, but further work is needed to understand what exactly happens, and this is ongoing work. So I'll stop here. Basically, here are my conclusions. I'll just leave them here. Thank you.
Okay, any questions?
Just a very quick one at the end there. Have you tried taking that travelling wave solution that you got from Basilisk and putting it back into your Stokes steady state solver?
Yes, so there is, we compared like our steady Stokes solver solutions with the traveling wave solutions from, oh, you mean for
the one
value?
that you got beyond?
No, I mean, somehow, I mean, we are doing some more simulations now, so maybe, yeah, but for the values below the critical one, we get
Fine.
very good agreement. Yeah.
Just as an initial guess, it might help you lock onto
Yeah,
the solution.
yeah, okay, we'll try things. Yeah, thank you.
Okay, I think we're probably out of time for questions, so let's thank Dmitri again.